This is part 10 of lecture 11 of ELEC5300. We're going to start our discussion of deterministic least squares with the problem formulation and the solution. So the problem with deterministic least squares is we have a bunch of measurements, y, that depend on some parameter x, and x is multiplied by a readout matrix H and then subject to some noise where we are going to assume that V is a zero mean. And so H is known, V is zero mean random noise, and X here is a parameter that we want to estimate from measurements Y. But because of the fact that V here is noisy, we have noisy measurements. On the other hand, we typically have more measurements then we have data to estimate. So here M is the number of measurements, N is the number of parameters we need to estimate, and M is bigger than N. So for example, here in this example, M was 3, so I have 3 measurements. I only need to estimate 2 things, x1 and x2. So if I did not have this noise, then actually I could, assuming the matrix here is at least rank 2, then I could perhaps estimate the x1 and x2 from y1 and y2, or y1 and y2 and y3, or y1 and y3, right? But I cannot do that because these have noise. But nonetheless, you can imagine that, well, if I had the let's say these two, I would have a square matrix, and I could somehow invert it, and so x would be some linear combination of y. And so what we're going to do is we're going to say, well, let's try to estimate x by a linear combination of y by this matrix B. Okay, so this matrix B is going to be some kind of 2 by 3 matrix in this particular example. So x hat here would be in dimension n, right, which is 2. B would be this kind of matrix here, which is n by m, and y is m dimensional. This is y. Okay, so we're going to take all of these measurements here and then combine them together to just get, let's say, 2 measurements like we have here, or 2 parameters. So how can we do this? Well, one way we can do it intuitively is just to say, well, maybe what I want to do is I want to find the x such that I minimize the error between what x predicts, right, through h, and what I actually measure. Right? So remember, these two are not going to be the same because of this noise term v. Right? But they should be close to each other. So I'm going to measure how close these are by taking y minus hx times transpose times y minus hx. And so this thing here is going to be a scalar, right? It's not a matrix, this is a scalar. Right? Because here I have a 3 by 1 matrix, right? As in the previous example, I had 3 measurements. So y minus h x transpose, and this is going to be a 1 by 3 here. Or 3, this is 3 by 1 and this is 1 by 3. And so this is just going to give me a little scalar here, 1 by 1. So I want this s, which is the total squared error in each measurement, to be equal to be as small as possible. So one way you can try to do this is just, well, let's just take this s and differentiate it with respect to x. So in order to do that, I have to expand this out, so I get y times y, y transpose times hx, right? Then hx transpose times y, so that's x transpose h transpose y, and then HX transpose times HX, or X transpose H transpose HX. Now I have to differentiate this with respect to with respect to X, right? And so here you can see when I differentiate this with respect to X, I'm going to get a, let's look at this one first. If I differentiate this one with respect to X, I'm just going to get H transpose Y. So I'm going to get the same thing here when I differentiate with respect to X, because this is just a scalar and these two are the same thing, just transposes of each other. So I'm going to get two of these, so minus 2 H transpose Y. And when I differentiate this is just like H squared times X squared, so I'm going to get 2 H squared X. And if I set this thing equal to 0, that's going to give me my estimate that minimizes S. And so now what I can do is I can just solve this one, move this one over to the other side, divide both sides by 2, right, and then invert this. Right, so X hat LS is just going to be equal to H transpose H inverse times H transpose Y, and that I'm going to call B0Y. So this is the function for B0, and sometimes this thing is called the pseudo inverse. Right? But again, this is going to be a 2 by 3 matrix. Right? So this H transpose here is going to be 2 by 2 in our example from previous. So here H transpose, if I transpose that, times itself. So this will be 2 by 2, right? So we can definitely take the inverse of that. And then this one here will be 2 by 3. Okay. So this is going to be a small 2 by 2 matrix like this. It's going to multiply a 2 by 3 matrix here, like this, and then Y will be 3-dimensional. Okay, so this whole thing will be 2 by 3. So here's just an example of how that looks with some matrices that have been kind of written out explicitly. Here I have Y is equal to HX plus V. Right, so you can see here I have 4 measurements but 2 things to estimate. Here the thing that I need to estimate is given by a function of Y where this is B0. This converts it from 3 dimensions into 2 dimensions. Right, and then this is a 2 by 2 matrix here, which I can actually invert.